Welcome, everyone. This is our third and our final, as well as our longest session on climate forecasting. So in this session, we aim to foster discussions about the advances and challenges in climate forecasting using machine learning from leaders in climate science from the industry and the national lab. We are really lucky to have a pretty awesome set of speakers lined up for you. And to begin this talk series, we will have a talk by Lester Mackey from Microsoft Research. Lester is a machine learning researcher at Microsoft, where he develops new tools and models and theory for large-scale learning tasks, driven by applications from healthcare, climate, recommender systems, and the social good. Lester moved to Microsoft from Stanford University, where he was an assistant professor of statistics and by courtesy of computer science. He earned his PhD in computer science and MA in statistics from UC Berkeley and his bachelor's from Princeton. So Lester, please take it away.
Well, thanks, everybody. I think I'm sharing my screen now. Let me know if you can see it.
Looks good to me.
Great. So I like stories more than talks. I thought I'd spend my time today telling you all a story. It's a story of machine learning and of climate and of the Wild West. And along the way, I'll describe some joint work with a number of awesome collaborators. So Jessica Wong and Paul Orenstein from Stanford, Judah Cohen and Carl Pfeiffer from Atmospheric and Environmental Research, and also Ernest Frankel from MIT. So my goals for the story are fourfold. I'd like to raise awareness about an important problem for water and fire management, that is the subseasonal forecasting problem. I'd like to give you an example of crowdsourced science. In this case, it's the Subseasonal Climate Forecast Rodeo. I'd want to point you to a rich data source that we've collected and released. So here's a link. It's a link to what we call the Subseasonal Rodeo dataset. And I want to highlight a few tools for machine learning that are particularly effective in this realm. Okay, so this story begins with this guy, Judah Cohen. He's a climatologist and the director of seasonal forecasting at Atmospheric and Environmental Research. And one day he came to my lab and said, Lester, I have a concern. And that concern is that our community is not making the best use of historical data in weather and climate forecasting. In particular, the landscape is entirely dominated by dynamical models, which are purely physics-based models of the evolution of atmospheres and of the atmosphere and oceans. And I'm not a, oh, I see a little comment here. Oh, post your questions. Okay, great. So I'm by no means an expert on dynamical models, but here's a cartoon for those who aren't familiar. The idea is that first we observe weather conditions today. And of course, we only observe those at certain points in space and time. And so then we need to infer conditions everywhere. So we have some way of doing that. We infer current weather conditions. And then, well, we actually know how physics works. So we know in some sense how weather should evolve over time. And so we can simulate future weather or climate by running forward a system of partial differential equations. Now, of course, we can't do this perfectly. And so what we do is we grid up time and space. We throw our initial data into a supercomputer and we use that to approximate what weather will look like in the future. So Discord has these equations. And of course, that has some limitations. And so one big limitation is chaos. Lorenz proved back in the 60s that if your initial conditions aren't perfect, if you have small errors in your initial conditions, they're rapidly amplified. So that by the time we're trying to predict the weather, say 2 weeks out, our predictions can be quite bad, quite poor. And so that puts actually a fundamental limit on how well we can do with these deterministic methods at predicting the future. And so, of course, we have a few ways of trying to get around this. And one is through ensembling. And in this context, this often means run your model with different initial conditions, perturb your initial conditions, run your model with different model parameters, because there are also some parameters that are inputs to the models, and use the outputs of those different models to capture uncertainty. In some cases, we'll average their predictions to get a better forecast of the future. And a second way in which one often tries to improve these models is by a procedure called debiasing, which really just means compare the predictions of your models to recent history and subtract away the mean of your predictions and add back the mean of the truth. So debiasing is a pretty simple operation, but in some cases, that's the full extent to which historical data is informing these dynamical model forecasts. Okay, so that was concern number one. And then Judah said, I have another concern, which is that our sub-seasonal forecasts are especially poor. So what do I mean by this? Well, I think most of us are most familiar with what we call weather forecasts. And these are basically predictions of the state of weather, temperature and precipitation, say a few days out. And so nowadays, these are pretty good if you're just predicting a day out or a few days out. By the time you're predicting 10 days out, these predictions are actually getting to be pretty poor. And you probably wouldn't trust weather predictions if they were being made, say, 20 days out. And it's worth saying that weather conditions rely heavily on just the initial weather that we see today. Okay, but at the other extreme, if you're trying to predict weather over years, years in the future or decades in the future, or even just seasons in the future, you're in the realm of what's called seasonal forecasting or sometimes just climate forecasting. And in those cases, your predictability is largely coming from global factors like sea surface temperatures around the globe or the state of El Nino. And you often get a boost in prediction accuracy for these climate forecasts just based on the fact that you're averaging over more time. So, predicting the average over a year is actually, in some sense, an easier task than predicting a single day's temperature because it's a less noisy quantity. All right, so in between these two realms, weather and climate or seasonal, there's what's called subseasonal forecasting. And this will roughly define as predicting 2 to 6 weeks out. And the problem with subseasonal forecasting is that it's at a time range when our weather models aren't very good, but we don't get the full bump in accuracy from averaging because it's still a pretty short time scale. We're only averaging over weeks instead of seasons or years. And so the subseasonal forecasts are typically the most inaccurate amongst the three types of forecasts that you might make. And they're also complicated because they depend somewhat on our initial conditions, like what the weather is like today, but they also, and local conditions, what the weather is like around the point at which we're making our forecast, but also on global factors like the sea surface temperatures and the state of El Nino. And so this is a particularly difficult problem and one that he thought we should try to tackle together, subseasonal forecasting. Okay, so for the purposes of this talk or this story, I'll say that subseasonal forecasting is predicting temperature and precipitation 2 to 6 weeks out. And you might ask, why would you want to do this? And it turns out these forecasts are already being used to allocate water resources, to manage wildfires, to prepare for droughts and rainfall, heavy rainfall, flooding, increasingly for farming purposes, and ultimately there's an intention to use it more for energy pricing. And so these are all reasons why you might care about tackling this problem. But then Judah said, well, if all of this isn't enough, there's also this poster that I found, which says, $800,000 in prize, $, saddle up for the subseasonal climate forecast rodeo. So that's a somewhat strange poster to see. Strange terminology, saddle up for the subseasonal climate forecast rodeo. What does that mean? So let's try to break that down. So this poster was actually put out by a government or agency of the US called the US Bureau of Reclamation. And the mission of the USBR, let's call it, is to manage, develop, and protect water and related resources in the Western US. So they actually manage water in 17 Western states. They provide 1 out of 5 farmers with irrigation water. They're the second largest hydropower producer in the US. And what they've noticed is that over the past 8 years, every state in the Western US has experienced drought, and this has affected both our local economies and our national economies. And so they want to do something about this. And to do this, they need to forecast, drought in the future. So to tackle this problem, they organized what they call the Subseasonal Climate Forecast Rodeo. This is a year-long, real-time subseasonal forecasting competition, and it was meant to advance science, to raise awareness about this particular problem, and also to provide an evaluation platform for subseasonal forecasting. So Western US, hence rodeo and saddling up. Okay, so in the rodeo, there were 4 separate forecasting tasks. 2 variables, you're trying to predict either average temperature or total precipitation, and then 2 outlooks, predicting weeks 3 and 4, that's 2 to 4 weeks ahead, or weeks 5 and 6, 4 to 6 weeks ahead. So each forecast period is a 2-week period, but there are 2 different outlooks and 2 different variables, so that's 4 forecasting tasks. And your forecasts were issued on a 1 by 1 degree lat-long grid. So that meant, these are the blue points in this map represent the points that you'll be forecasting, and there are 514 in total across the Western US. And then you would issue a forecast every 2 weeks. So this ran from April 2017 through May 2018. You were disqualified if 2 submissions were missed during that year-long period. And so that was pretty harsh. You know, 1 submission was on Christmas Day. But for many, that was just motivation to automate your forecasting procedure ahead of time. And then you would upload your forecast in the form of a .NET-CDF file to their server, and that would be scored once the future was realized. Okay, so that's the setup for the challenge. How were contestants evaluated? Well, for this, we're gonna need a little bit of notation. So for each 2-week period, starting on a date T, let's define month day of T as the month day combination associated with that date. So for instance, January 1st. Now associated with that date are our observed outcomes. We'll call those YT. YT is a vector because we're making 514 predictions. Remember G, I'll call G 514. So G predictions, 1 for each grid point. And so the vector of outcomes is in some sense what you're trying to predict. It's going to be average temperature over those 2 weeks or total precipitation. But in this contest, you don't want to predict outcomes directly. What you're really interested in are what are called anomalies. So your anomaly is the difference between your observed outcome and in some sense your best guess at what that observed outcome would have been based on recent history. That best guess is called climatology. So you compute the average temperature, we'll say, on January 1st over the period 1981 to 2010. That's your baseline. And what you care about is your fluctuations around that baseline. So is it going to be much warmer than climatology or much colder than climatology? And so your anomaly vector, AT, is what you care about predicting. It's the difference between your observed outcomes and this climatology. All right, so now how are you evaluated? Well, the measure for this competition was actually somewhat unusual from a machine learning standpoint. It was what's sometimes called skill, forecasting skill, and specifically it was cosine similarity. So it's cosine similarity between true anomalies and your forecasted anomalies. You know, it's a measure of like the angle between your vectors, if you think of these as big vectors in R to the G. All right, and so this is a number between -1 and 1, somewhat unusual. It's also a multitask objective, so it's coupling together each of the 514 different prediction problems into a single measure. And so that's going to inform some of the methodology that I mentioned later on. But that's the setup. Your goal is to have good skill. Good skill means skill that's close to 1. Okay, and to do well in this contest, to be rewarded with some of those prizes that I described, you had to outperform 2 benchmarks. The first benchmark is one of these operational physics-based dynamical models that I was describing. In this case, it's called the Climate Forecasting System V2. I'll call it CFS V2 for short. It's the United States operational forecasting model for subseasonal forecasting. And in this case, the benchmark is actually an ensemble of 32 different versions of that model. That's 4 different model initializations at 8 different lead times, averaged together. And then on top of that, they did this debiasing step that I mentioned. So they looked over the period 1999 to 2010, subtracted away the mean of their model, added back the mean of the truth. And that had a huge effect on performance. The skill was actually quite terrible before they did that and improved it significantly. And that was one of the baselines. The second baseline was called damp persistence. Apparently, this is a very standard statistical forecasting model, except we never got any very clear description of what this model was, and we could never recreate it. So we actually don't know what it was, but this was a description that we got. I've quoted it here for you, some sort of seasonally developed regression coefficients based on the climatology period. So you can think of it as some statistical model that uses lagged temperature, say, to predict temperature. Okay, so I've thrown a lot at you. In case you want to see what all of this looks like, here are some visualizations, both of the forecasts that we made during the competition and what different levels of skill represent. So on the top left here, I'm showing you a forecast that we produced. On the top right, I'm showing you the truth. And this is displaying temperature anomaly. So red means hotter than expected, and blue is colder than expected. The bottom left is the forecast that was made by CFSV2 for this particular date, and the bottom right is damp persistence. So you can see a few things. First of all, our skill, so our forecast looks something like the truth, and indeed, in this case, it has a skill of 0.83. So that means it's essentially very correlated with the true vector of anomalies. And this is an example also where CFSV2 has very poor skill. It's predicting cold, basically where it should be hot. It actually has negative skill in this case. And, you know, this is my talk, so I picked this example. I thought it was a good example. And the bottom right is damp persistence. For most of the competition, we actually couldn't see the forecasts. It has something to do with the fact that, like, of the granularity at which they're displaying colors on these maps. And so we should just ignore it for now. Wouldn't be worth evaluating for you here. So this is what a temperature forecast look like and what different levels of skill look like. Here's the same thing for precipitation. Top right is the observation, top left is our forecast, bottom left is CFSV2. Here, blue means wetter than usual, and brown means wetter than expected or drier than expected. And on the top left here, you actually see an example of essentially zero skill. This means that essentially our prediction is orthogonal to the truth, which is also not good. But in this case, also CFSV2 had negative skill again, so minus 0.2, and it's basically predicting a lot of dry in Texas where it really should be quite wet, and that's why. Okay. So, right, so I described a task. Now the question is, you know, what data do you use to solve this problem? And an interesting aspect of this competition was that, like, no data was provided. The organizers did, of course, identify how they would evaluate your prediction. So there are certain sources that were being used to evaluate temperature and precipitation predictions. But otherwise, contestants were encouraged to use whatever data they wanted. And so what could you do? So if you use standard physics-based models, you had to demonstrate significant improvement upon those models. You couldn't just, you know, download CFSV2 and forecast that every day. But otherwise, you were free to do whatever you wanted. And so what we did was we went to lots of websites. We downloaded and scraped whatever publicly available data we could find that we thought was relevant. And we constructed what we now call a subseasonal rodeo data set from these different data sources. And, you know, every data source had its own format and its own granularity, both in terms of time and space. So we put them all into a common format, common, you know, daily granularity, put them up on the Harvard Dataverse and as a set of pandas HDF5 files. So you can now download them and use the pandas data frame to, you know, benchmark and train your own subseasonal forecasting models. So I have a link here if you want to check that out. And, you know, there's a great variety of data sources. So we have temperature, precipitation, those are key, but also data sources like pressure, sea surface, sea surface temperatures. We have some very coarse-grained model forecasts from the North American Multi-Mean Ensemble, State of El Nino, Madden-Julian oscillation, that's all in there. Okay, so what did we do modeling-wise? We took basically two approaches and then ensembled them. And so I'll just very quickly describe what those approaches are. One, we call it multi-LLR, so it's multitask locally linear regression. This basically takes in lag measurements from all the different data sources that I mentioned, combine, and because not all features are actually relevant at all times of year, so for instance, sea ice concentration is less relevant in the summer than it is in the winter. So it prunes out irrelevant features using a specific multitask feature selection procedure that's targeted toward our skill-based objective, and then it fits a local linear regression on top of that. So that's multi-LLR. Our second approach is much simpler than the first. So instead of using all of these diverse features to inform our prediction, if we're predicting temperature, we're just going to use past temperature data. If we're predicting precipitation, we're just going to use past precipitation data. We look for days in the past that we think are most similar to the day we're trying to predict. The similarity measure basically is how well does the history of that date predict the history of our target in terms of skill. And then we pass all those features into a weighted locally linear regression. So we pass the observed temperatures from the most similar dates into a weighted locally linear regression, and we combine them to form the forecast. And then finally, we ensemble together those two predictions in a particular way. We L2 normalize, so we normalize the vectors of anomalies and we average. And we do this because it turns out that for skill, for cosine similarity, if this can only improve your skill. So if the average of your skills was positive, the skill of this average will be even better. Okay, so let's just look at some results. I see I'm getting some chat comments. Okay. 3-minute timer. Oh, great. Okay. Quickly, as mentioned, results. What do we see here? So this is the evaluation over the course of the contest period. Remember, there were 26 observations over the course of a year because you make one forecast every 2 weeks. I'm showing you the average skill of these different methods. What you can see is, here are the two baselines, the bias CFSV2 and damp persistence. What you can see is that each of the methods I mentioned, multi-LLR and AutoKNN, are better than each of the baselines. So that's great. If you ensemble them, you get a big boost in performance to the point where they're better. The ensemble is better than the baselines, and it's also better than the top competitor in the competition for each of these 4 tasks. It's worth saying, though, that the competitors in the competition were doing this all real time. Their strategies might have been evolving over time. Here, I'm just evaluating a single strategy over the course of the contest period. On the top, you can actually see histograms of performances across each of the biweekly periods during the competition. And mainly what you see is that the baseline procedures tend to have a lot of extreme negative skills, which counterbalance the positive skills that they also have. And so CFSV2 in particular often has either very positive skill or very negative skill, and it's hard to anticipate which one it will be. And on average, the skill is poor because of that. All right, and you can also evaluate this over the course of all years since climatology at the time of the competition. So it was 2011 to 2018, and you see something very similar. Each method is essentially doing better than CFSV2. The ensemble does significantly better than CFSV2, improving over the operational model by 20 to 38% for temperature, over 120% for precipitation. But then, if you also ensemble in CFSV2's predictions, if you do a 3-way ensemble between multi-LLR, AutoKNN, and CFSV2, that has an even bigger boost, which means that our machine learning models are still not capturing everything about the physical models, and the physical models are providing something complementary. So that was very interesting. And maybe I'll just close by just pointing out some aspects that were learned by these models. The multi-LLR model, I recall that this is doing feature selection on each day. So each day it's choosing a different subset of input features to use for its prediction. And so you now can rank order features by their frequency of inclusion over time. And what we find is that pressure and lag temperature are in the top 4 features for all 4 of our prediction tasks. That is both for precipitation and for temperature. And that the physical models, the NMME models that I briefly alluded to, are pretty frequently selected for precipitation tasks as well, although much less so for temperature. And this is because the accuracy of these models is actually quite low compared to say just using the lag temperature. But the precipitation task is actually quite a bit harder than the temperature task. And so those low accuracy features still add a lot of value. Okay, I'm not sure how much time I have left. Perhaps none. Let me leave you with one final thought. I think I might be at the end of my time. So I wanted to say something about the AutoKNN method. Let's see, here's a chat. Oh, okay, lots of great questions. All right, one quick thought about the AutoKNN method. So with AutoKNN, we're actually picking the most similar dates in the past, so you can actually visualize for any given time of year, which is what I'm showing at the top part of this circus plot, at what time of year is its most similar neighbor. And what we find is that for precipitation, the top neighbor tends to be from a similar time of year. So if your target date is in January, it tends to pick past Januaries or Decembers as top neighbors. That's actually not true for temperature. For temperature, your top neighbors come from all different times of year, which I thought was a bit surprising. But that is true for precipitation. But then maybe I'll stop there. I'll say that if you want to learn more about this, you can read our paper, which published at KDD. You can read more about it on arXiv. You can learn about the data set there as well. And I'll take some of these questions that I see popping up.
Perfect. Thank you so much, Lester. This was a very enlightening talk. Since we are running a bit behind schedule, I would just take one question from the audience for now. And if you would be kind, just interact with the audience in the Zoom, that would be wonderful. So I'll take a question from Owen. And he says, could you please explain your reasoning at arriving at the at the models you have used, why did you choose the models? Why did you choose the models that you did? And why does this work better than neural networks or Gaussian processes? That is fairly common in machine learning.
Yeah. So I should say that the models I presented here today are the ones that, yes, that we found to work best. They're not the only ones we explored. We did explore neural networks. We did explore some Gaussian processes, some clustering approaches. These are the strategies that empirically work the best. Each one was motivated by some particular intuition that we had. So the AutoKNN was motivated by this method of analogs that is a relatively common method in forecasting, which is, look for dates in the past that are similar.
Sure.
The idea here is that we're trying to capture similar patterns. In fact, if you just do that alone, though, if you just look for dates in the past that are similar and then use their forecasts, they actually perform pretty poorly at this task. But if you combine the predictions of these similar natures in some sort of regression, then it works quite well. And I found that it also works well in other tasks, and say like recommender systems, and that's what the motivation of that particular method. And the other was motivated largely by this idea that there are lots of features that are potentially relevant. The relevance of those features differs from time point to time point. We want to do some sort of model selection that would incorporate the skill objective directly, and that led to the multi-LLR. But in some sense, that was the simplest version of that method. You could do multi-blank, you could do multi-neural network or decision, random forests. And so that second stage is open, but we did try other procedures, but they actually performed worse. So a big part of that was empirical. Yeah.
Interesting. So thank you so much, Lester, again. Really appreciate you coming out here and giving us this wonderful talk. So I'll move ahead to the next speaker, and I would encourage you to, the audience, to post their questions for Lester in the chat so that we can all take a look. So the next speaker for us is Dr. Balu Nadiga. Dr. Nadiga is a scientist in the computer, computational, and statistical sciences division at the Los Alamos National Laboratory in northern New Mexico. His research interests are at the intersection of statistics, machine learning, and climate physics. He has made seminal contributions to the advancement of the state-of-the-art in climate forecasting. He obtained his PhD from Caltech, and following which he was a research fellow at UPMC in Paris, as well as a visiting scientist at MIT before he started at Lionel. Dr. Nadiga,
Can you see my screen?
Yes, we can see your screen, and we can hear you as well.
All right. I'd like to thank the organizers for the invitation, and I'm happy to present some work on learning to predict spatiotemporal variability of climate. In the previous talk by Lester is a good lead-in. And to put this in perspective, it was the decadal forecast that he was talking about, the one which comes at the longer time scales. And here are some of the people who have been involved in this work. And I want to keep this talk, since this is a machine learning conference, I want to keep this talk in a more general fashion and spend significant amount of time in the problem setup, more in the sense of fostering more interactions later. And I'll confine the deep neural network results to a slide or two, and then because I'm assuming that a lot of you are familiar with it. So here is an outline of the talk. I'll start with a 5-minute climate tour, just to give you an overview of what space we are operating in, and then an even shorter climate modeling tour, right, as to how the models address modeling the actual climate system. Then I'll spend a little bit of time on saying what prediction is and what predictability is. And then I'll, as you can see, going down the list, it is getting more and more specific. So I'll talk of two kinds of predictability: the external forcing related predictability, the kind of thing that you would expect from an increase in carbon dioxide or greenhouse gas kind of a scenario, and then the more pernicious, more difficult natural variability related kind of predictability. And that is, second one is what you are familiar with in the weather context. Okay, and then drilling down, getting more specific, I'll talk of the difficulties with predicting natural variability, and then move on to the actual results, some of the results in terms of deep learning, spatiotemporal variability of climate on these time scales. And then Of course, this is a very preliminary work, and I encourage anyone who is interested in these kinds of things to get in touch with me. But, there are significant difficulties, even with the DNN, deep neural net kind of an approach, and transfer learning is one of the tools that is likely to play a key role in this kind of a work, and then I'll summarize. All right, here is a 5-minute climate tour. So there is the surface of the world here, and you should think of this as the vertical. So it is a cartoon, and the global climate system is driven by insolation from the sun, which is huge, and then there is a lot of feedbacks and other kinds of things, which essentially has to result in as much energy essentially going back. So there are large energy fluxes coming in and going out, and the small differences are what causes warmings and changes from equilibrium states, for example. And so that is the primary driver, so to speak. Yeah, but it so happens that the Earth is spherical, so the equatorial and the tropical regions receive a lot more insolation than the polar regions, as you can see here in the purple line. Whereas if you look at the radiation, the long wave radiation away from the Earth, it is far more uniform than the short wave incoming radiation, which means to say that the poles are warmer than you would expect from a radiative point of view. And so indeed, this extra energy that is present here in the equatorial tropical regions has to be transported to the polar regions to make the mid latitudes and the polar regions more habitable. And that is essentially what drives the climate engine, so to speak. And in a large fashion, you can think of this as a heat transport problem. And the way this heat transport is achieved can be extremely complicated. It results in a lot of motion called this general circulation in the atmosphere, in the ocean, and things like that. And that is the object of, again, this is, in the interest of time, let me skip that. But as you all know, this is from Mauna Loa, a series of carbon dioxide, time series of carbon dioxide as a function of time, starting in 58. And as you can see, there is a seasonal cycle to it, but there is a large secular trend to the carbon dioxide given the use of fossil fuels. And then you have the temperature and salinity, so acidification going on. These are observations. I'm sticking to the actual climate system right here. So if you dig down deeper, meaning to say both literally and figuratively, you can go to the ice cores and you can get proxies, and you can get proxies for carbon dioxide. So over a 2,000-year period, this is the kind of time sequence that you see. Our period being a period of unprecedented growth in carbon dioxide, and even longer, over 800,000 years. From the Antarctic ice cores, Dome C, so-called Dome C, you can see the presence of these 100,000 year ice age interglacial cycles, but never did the carbon dioxide levels go much beyond 300 parts per million. And so the Earth system responds, and this is how it has responded in the last 200 years or so. And you see the steady increase of temperature. Okay, and if you go to this site, you can also see the reconstructions or video of the reconstruction of temperature record across the globe, meaning spatiotemporally varying. And this is the kind of warming that we have seen with respect to 1951, 1980 average. So lots of warming over land, significant warming, but very heterogeneous warming overall. All right, so now next to the climate modeling aspect of things. And these climate models are extremely complicated. They essentially try to do everything that the Earth system, the hope is to try to do everything that the Earth system does. The build bottom up by putting down the governing equations as we understand them. And if we cannot resolve the process, we end up parameterizing these smaller scale processes because of computational requirements. You cannot solve all the scales in this strongly coupled multi-scale system. these are indeed the best tools to understand climate and modern climate and its variability and its change, but it is extremely demanding. It requires entire modeling centers, in national and international centers, to run these, develop, run these models, analyze them. All right, so again, this is what they try to do. They essentially try to capture all of the feedbacks, essentially capture all of this heat transport in the horizontal and the vertical, and then produce responses such as this, the famous hockey stick kind of a temperature response. Okay, that's the 2-minute modeling tour. So prediction and predictability, I mean, this goes back to Lester's talk where he was talking of weather forecasting. So weather forecasting can be identified as the process of determining how the weather will change as time advances. But what is predictability, right? And predictability is the field of study which tries to understand why and how long such predictions are possible. Okay, this is most of this work on prediction and predictability traces back to Lawrence at MIT, who indeed was also the discovered chaos, the sensitive dependence and chaos and all of those kinds of things. So just to distinguish weather and climate, again, going back to one of Lester's slides, weather is often identified as the complete state of the atmosphere at a particular instant. So it is an extremely detailed description. Whereas you can think of climate as the statistics of ensemble of all states during a finite span. This finite span in general can be thought of as a few years up to about 30 years. So then climate prediction becomes the question of determining how the statistics will change. And then climate predictability becomes a question of trying to understand why such predictions are possible, right? I mean, in large part, there are, so to speak, to have a simple picture in the back of your mind, there are some self-consistent oscillations in the climate system, internal oscillations in the climate system. I mean, it is far from as simple as that, but that is the cartoon kind of picture that you can keep in mind, which so if you can initialize yourself on the correct phase of some such oscillation, then you can predict climate for some amount of time. That's the kind of simple picture you want to have in the back of your mind. Okay, so drilling down further into predictability, there are two kinds of predictability. One can be thought of as forcing related predictability, like, for example, what will happen to the climate system if you increase carbon dioxide in the atmosphere. And then there is the issue of natural variability related predictability, meaning to say, if there was no change in external forcing, can you predict climate over a few years, right? And these are going back to the oscillation kind of a picture. And of course, these are only simplifications, and these two always act jointly. So as far as the external forcing related predictability is concerned, we are pretty good at being able to realize that predictability. And that is what gives rise to being able to believe in the kinds of projections that models produce. For example, here I'm showing the surface temperature globally averaged as a function of time, and also as averaged by a number of models in, for example, the assessment report 5 of IPCC. So this is a well-developed activity, and we have belief in being able to predict long-term global kinds of averages, say, for example, on the 30-year time scale. Again, just to be clear, I'm showing here that surface temperature changes, but it is very important to note from a dynamical perspective that as much as 93% of the excess heat due to the greenhouse gases is actually taken up by the world oceans. Okay, so what you're seeing here in these kinds of projections is typically due to 4 or 5% of the excess heat due to the greenhouse gases. But we live on the surface, and so anthropocentrically, we tend to focus on that kind of a measure. Okay, and because the ocean takes up so much heat, it can have lots of effects, including rises in sea level and things like that. And in particular, it also has an important effect, for example, as shown here, on the sea ice, extent of sea ice in the polar regions. And in particular here in the Northern Hemisphere, you see that in as few as 30 to 70 years, you can see that the Arctic can be ice-free in the summer at the end of September. All right, so next I want to talk about why it is difficult to predict natural variability. I think just in the interest of time, I'll go a bit quicker here, but the bottom line is that there is this sensitive dependence on initial condition as engendered in this schematic here. So if you estimate your state of the climate system currently to be like this, and then advance it in time over a few years, then you have a large factor of uncertainty here. So the ensemble average tends to be observing the Earth system to estimate the state, and then conducting these large-scale ensembles is the crux of the problem. Is the main modeling tool, so to speak. Again, I'll be happy to talk about these things in more detail for the interested people. So again, the thing is, there is a very delicate and intricate balance of a myriad of physical processes in the climate system, which gives rise to the observed mean state of the climate and its variability. And it is extremely difficult to model this exact balance in the model climate system. So a fact of the matter in modeling climate is that there is going to be this kind of a bias here. And so when you have this kind of a bias, this bias completely messes up with this ability to be able to predict climate on the decadal scale, meaning to say you spend a lot of effort. So we are interested, for example, here in predicting the evolution of this black line, starting from say here. So you spend a lot of infrastructure observations, estimate the climate system to be at this point in 1972, for example. Again, this is just a cartoon. And so once you initialize there, because there is a bias in the climate system, and this is a chaotic system with a chaotic attractor associated with it, the immediate thing that it does, it is rather than follow the observations, is for it to jump away and seek its own attractor, fall back onto the attractor. So I can get into the further details of this for the interested people later on, but this is in some sense the problem. The dynamics of this drift can be so pervasive and pernicious that it can actually completely defeat any of these interannual predictions. There are some statistical ways of addressing this issue, but it is statistical for a reason. That is because we cannot actually address the underlying problem. Anyway, so this is indeed the case here. So I'm showing just an example here in a couple of models. And when this is the observed kind of a time series that we are interested in, you start these initial predictions here, and you see that right away it jumps away from it and follows its own trajectory, right? And this is very similar across dozens of models, and for example, in the IPCC analysis of things. All right, so that's why I want to, I mean, in some sense, more of a hobby to try to look at what deep learning may have to offer in a setting like this, as to whether we can actually take the route of deep learning spatiotemporal variability of climate to be able to better predict it on the interannual to decadal time scale. All right, so here are some details of the particular setup that I'm using. And so here I'm using an IPCC class model. It's a very popular NCAR CESM2, the latest NCAR community Earth system model. And obviously the seasonal cycle is easier to predict, so that has been removed. And the effort consists of formulating the problem with very different, in a multitude of ways, and use very different architectures, and then look at them from the perspective of what we are able to glean from this kind of an effort, right? And then future things will be to try to understand, based on this deep learning approach, where the predictability is coming from. Okay, so I think I'll go through this rather quickly, but there are various approaches, including convolutional LSTM, the long short-term memory things. Then there is the PCA kinds of analysis that you can exploit to try to represent the spatial component of the variability and things like that. So again, without getting into very much of the details, I'll show you just a couple of results on this case. So this is one of those ways of predicting the spatiotemporal variability of climate. And you can see that it produces meaningful results. And in a sense that these are physically consistent. The errors are greater at the mid and high latitudes, errors are greater over land, and there are various reasons you can attribute to this from a climate perspective, climate dynamics perspective. And so this is one of the things that surmises a lot of the work perhaps over the last year or so. So the idea again here is to try to look, I mean, I've purposely formulated this problem in a very difficult way to be surprised if deep learning can afford surprising results. But as you can see here, for example, some of the models that I'm using here are simple ones like the multi-layer perceptron, the LSTM, or the PCA LSTM, or and the convolutional LSTM. Again, I have various other variations which use attention and various other aspects of RNNs, but I won't get into the details here. But this one, if you were to come at it purely from a statistical perspective, this is a statistical model. So this is the plot of normalized error as a function of lead time. And you can see that this is my baseline reference that I want to beat, right? I mean, this comes purely from a statistical point of view in terms of covariance analysis. And you can see that as you increase the complexity of these deep neural networks, actually, it begins to outperform the statistical methods, at least at a significant fraction of the lead time. So, I mean, this is ongoing work, and the flavor of that I want to convey is to see if these deep learning methods can actually significantly improve on the kinds of predictions that we expect out of the system, and then to reason about that kind of analysis. You can see here that the predictability does not go significantly beyond about a year or so, as would have been expected from the statistical analysis itself. Okay, so again, so just to put this in perspective, here I'm using some reservoir computing in a chaotic system, and this is the full system. And I'm plotting here the normalized error as a function of prediction lead time. And this is non-dimensionalized by Lyapunov time, which you can roughly think of as the error doubling times. So I'm using I'm using a form of neural networks here called the reservoir computing, which you may be familiar, but without getting into the details here. And remarkably, you can follow this trajectory through its various switches across attractors for as long as about 10 Lyapunov times. I mean, it is quite surprising in a sense, and this was some very exciting news in a couple of years ago when this was first found out. And then later on, you see that there are actually, it begins to deviate away, and because it's chaotic, the deviation can be quick and then dramatically follow the wrong attractor, for example, as you can see from the dissonance here, right? So this is indeed a very surprising and a very strong result coming out of deep learning. And so this is how the divergence happens. But I want to highlight one important thing here. Even in this nice system, again, I'm plotting RMSE as a measure of skill, as a function of prediction time, non-dimensionalized in terms of Lyapunov times. And as you can see here, if you observe the system fully, as in this rightmost thing, you can get to as long as 10 Lyapunov times. But if you degrade the observation of the system, if you systematically degrade the observation of the system, then you see that the predictability, the predictions that you get from this deep learning kind of an approach quickly degrades, and you practically have very little predictive skill when the observations become sparser and sparser. And the point here is that it is very difficult to get a very good estimate of the climate system, meaning to say the observation is only partial observations are possible in the first place, and even getting a reasonable estimate of that is a very difficult thing. So this gives you an idea of how important observations can be. And so in a sense, transfer learning is clearly a tool in this kind of a setting, but it is surely not going to solve the sparse observation problem, for example, as exists in the climate system. So here is a summary of the work. The predictability studies have typically been considered in a perfect model setting, and because of this kind of study, people have expected that there is predictability that extends to the decadal time scale. However, if you actually examine the state-of-the-art climate models, there is much less predictive skill. It is, while people talk of the decadal predictability, there is very little of that has actually been realized. And model bias is one very important reason for this kind of loss in predictability, observations being the inevitable other one, right? But this is something that we can work with. But again, one has to be realistic in and note that it is very unlikely that model bias will ever go away, right? And so the question tends to be in a big sense, in a broad sense, what do data-driven models have to offer in this setting? And so one way to go about this is to develop learning-based prediction system and see if they can actually match or improve on the climate models, for example, but at the same time making use of climate model data because the observations themselves are sparse in the transfer model sense. And again, these are tasks to be done. And again, I'm very interested in the machine learning experts here who may have interest in these kinds of things and further ideas on how some of these problems can be addressed. Thanks.
Thank you so much, Dr. Nadiga. That was an excellent talk, an end-to-end introduction about climate science and your leading efforts in this area. So we are short on time, so I'll just stick to one question from the audience for now, while I'll encourage everybody to keep posting their questions here. So there's a question for you from Lauren Kunz. And Lauren says, should we be concerned that almost all of our climate models do recreate historical temperature trends, including multi-decadal variability, especially the mid-20th century warming hiatus, and don't show the bias you talked about? Might that indicate that we are overfitting or using external forcing that are poorly constrained, like volcanoes, to capture the historical trends?
Yeah, I think that's an important question. The whole question of tuning. So there is an extensive amount of tuning that goes on with the climate models, and everyone is cognizant of that. But it is a good faith best estimate, right? I mean, no one is. I mean, there may be unconscious biases in this, in some sense, but I mean, this is a good question. But I don't know. This is an open question, and I don't have a good answer. So there are issues with tuning, but that's the best we can do right now.
Okay. Thank you so much, Dr. Nadiga, once again. And just as a note to all the participants, we are running a little over time, so we have decided not to do the breakout session while we have as in our agenda. But instead, we will have a Q&A with our speakers, Dr. Nadiga and Lester, as well as Campbell and Adrian coming up. So please continue to post your questions in the chat and interact with our esteemed speakers. So so now I'll move on to the next speaker, and our next speaker for this session is Campbell Watson. Okay, where's the intro? Okay, so Campbell Watson is a research staff member at IBM Research in New York. He's part of the multidisciplinary team developing an experimental modeling and observational platform for freshwater and coastal environments, and helping lead a new climate initiative focused on modeling and prediction. He was recently awarded an Outstanding Technical Achievement Award, IBM's highest technical award, for his work with the Deep Thunder Weather and Climate team. Campbell studied atmospheric science in Australia at the University of Melbourne and moved to the United States in 2012 for a postdoc at Yale University. So welcome, Campbell. We look forward to your talk.
Hi, thanks everybody. I hope you can hear me okay.
Yeah,
so great. So I'm at IBM Research, and this next slide shows you all of the different research labs around the globe, which really blew me away when I first joined IBM. So I'm currently working closely with people in Brazil. I'm actually based here in what they call the Watson lab, even though I'm no relation to the Watson that it's named after, which is just north of New York City. So I'm working with people in Brazil, in the UK, and also starting to work with some folk in Africa in the Kenya lab as well, which is really great. I'm originally from Australia, but I've been in the US for quite some time now. IBM Research it's vast. There's a lot of research groups. There's a lot of different focuses, and I think a really wonderful thing is that there's quite a bit of environmental research work going on. There was a talk earlier this week on Saturday at this exact conference by the group in Kenya, and that was looking at safeguarding continuous water supplies in northern Kenya. And I encourage you to reach out to Fred, or you can actually catch the work through the website. There's malaria modeling and climate that's been happening out of the UK lab. That's been, I think, in collaboration with the Bill and Melinda Gates Foundation. I'm personally involved in this project here, this potential drivers for harmful algal blooms in New York State lakes, and I'll be talking about some of the lake work that we've been doing and some surrogate modeling. There's soil moisture predictions related to agriculture that's coming out of the India and Brazil labs. And a lot of this is now feeding into the weather company, which, as many of you know, is now part of IBM. And the weather company are very much focused on weather. They have their seasonal forecast that extends out to 6 months. And that is a pretty firm stop for them. An exciting thing for me is that IBM Research is starting to consolidate work around climate. And that's, if you look down at this slide here, it says Impact Science, Future of Climate. It's sort of under this umbrella. And it's to me, I'm looking forward to the next few years of work. To my surprise, and I'm sure to the surprise of many of you, IBM has been involved in weather forecasting since 1996. And this was for the Atlanta Olympics, and it was running a precursor of the WRF model, which some of you may know, which is kind of the standard weather model these days that's being built from the US. It's called RAMS. It was run on a 30-node supercomputer at 8 kilometers resolution, and these 3-dimensional visualizations, animations were produced for the actual opening ceremony of those Olympics. And I think that was a real feather in the cap of the people that were involved, including my boss. I was still in high school at the time, as you can probably imagine. The project that I'm specifically on and have been on for quite a few years now is called the Jefferson Project at Lake George. And this is a multi-year partnership. It's so IBM Research is one of the partners. Rensselaer Polytechnic, which is a university in upstate New York, is also involved. We're working closely with their biology department, and the Fund for Lake George, which is an advocacy group. And the broad aim of the project is to understand and manage the complex factors threatening Lake George. We're monitoring, we're modeling, we're managing and predicting. So we've got a whole lot of weather stations and vertical profilers out there, stream gauges, and there's a field team that go out sampling the lake, getting samples of phytoplankton, for example, doing fish surveys and so forth. I'm personally involved in the operational forecasting system, which is coupling weather models with land and hydrology models and a lake circulation model. I'll be presenting some work today on the lake circulation model that we're trying to represent with artificial neural networks. And this is all tightly coupled in with an observing cyber infrastructure. And I'm just going to add The part that excites me the most of this whole project right now is this nutrients model down the bottom. So this is trying to simulate the nitrogen, the phosphorus, and zooplankton and detritus circulating through the lake. And that's going to be a really key ingredient for harmful algal bloom prediction going forward. So I thought I'd add that in. The lake circulation model we're using is called SUNTANS. It's the Stanford Unstructured Grid Non-Hydrostatic Parallel Coastal Ocean Model. And so it's really designed for places with very complicated shorelines like the coast and also like lakes. It's 3D finite volume and it's an unstructured grid. So it's triangular cells and it's 3D. So there's also these Z layers as well. So if you can imagine an animation, 3D animation, you're seeing water moving through that entire volume of water. Go to the next slide. And this here is some validation to show you that SUNTANS, the lake circulation model, is doing what we expect it to do. And so we have a vertical profiler, which effectively goes up and down through a vertical column of the lake, sampling the water temperature along with a few other things in the southern part of the lake. And over time, we can produce a picture like this, and you get an idea of how the temperature is changing in this southern part of the lake. And the model is predicting very closely these temperature contours, including this event that happened here, which is a downwelling event of sorts, where it was related to a strong wind burst over about 24 hours. Anyway, I just thought I'd add that in there. This is not relevant to the rest of my talk. What I will be focusing on is surrogate modeling with artificial neural network reduced order models. And the aim is to approximate the SUNTAN solution with a fully connected neural network and an LSTM, reduced order model. And so reduced order models are simplifications of high fidelity complex models. In this case, we're doing POD or PCA to try and reduce the complexity of the solution. The FCNN is a fully connected neural network, and the LSTM is a long short-term memory. I'll be presenting results mostly from the fully connected neural network today, because I think the workflow is a little more interesting than the LSTM. The results were very similar, though, that we ended up getting. This work has been submitted to CFDML, and we're waiting on reviews of that. And I need to stress that this was led by my colleague Alberto in the Brazil lab. He should be online, and if you have any questions as this talk is happening, I'm sure he's happy to jump in and try and answer them. So, okay, I will move on. So the data sets that we're using, we have weather data and we have lake circulation data. Here, what we're calling the truth is the SUNTANS, is output from the SUNTANS model with the lake circulation. We're just trying to recreate the model. We're not really trying to recreate observations per se. So the inputs are from the WRF model. We have air temperature, pressure, and U and V wind velocity. And these are just 2D surface values. And the targets are from SUNTANS. We have water temperature, density, and the U and V water velocity. It's really important to stress these are 2D depth averaged values. So we are not trying to represent the entire 3D lake circulation. We're just trying to get the depth average values for now. There's some thoughts of extending this work to look at, extend it to maybe 3 or 4 discrete layers of the lake, which would probably make more sense from a hydrodynamic standpoint. But this work is just looking at the depth average solution. For training, we've taken 19 daily forecasts. Each forecast that we run is 36 hours long. So if you can imagine, it's 19 individual day-and-a-half forecasts. And for testing, it's just, we're trying to recreate one forecast. So this is, I think, a limited amount of data that we're training and testing on. But it gives you an impression of what the possibilities are with these frameworks. The dimensionality reduction for the reduced order model, we're looking just at the 5 highest energy modes, and that takes into account, I think, 98% of the variability for SUNTANS. And we have an accuracy target of the 5% of the 5% error in the L2 norm. And again, it's with respect to SUNTANS, the full order model is what we're trying to recreate. This here is the workflow of the fully connected neural network reduced order model. So for starters, there's the input data, which is I guess the training data sets, which are coming from Suntans. It's 19 days worth of forecasts. We decompose that into mean values and perturbations, Q bar and Q dash, and then compute the POD correlation matrix of the perturbation. And this, highlight this integral here is required because we're dealing with an unstructured grid. So each grid space has a different size, so we need to integrate over this area. Then we then we actually have the PODs, and we compute the spatial modes and time coefficients. With these time coefficients, we can send these into a neural network. This is where we're trying to get the neural network to estimate the time integrals, the say dc dt here. And we're also evaluating them numerically with the Finn difference method, and that's to come up with the loss function. And so this is where the hyperparameter optimization takes place. Then we have our trained model, and we can do a field reconstruction, which then produces effectively the approximate representation of Suntans. So this is the idea. Before we kind of jumped into going full ball into a very complex, non-linear lake circulation model, we started with the Lorenz attractor, and it's, I guess, something of a sanity check. And so there were two different modes that were studied here. One was the stable system, and one was the chaotic system, changing the value of rho to 14 and 28. What we found was that the FCNN ROM predicted the stable system really well. It converged on a solution relatively quickly. Two different optimizers were needed to converge, and you can see the pointwise error really reduced over time. The chaotic system, however, there was never really any convergence of the error. This orange line here, beneath this is actually the blue line, which is the target. So the absolute values of this derivative series are really good. The comparison of the absolute values look great, but if you look at the pointwise error, because the absolute values are quite large, we really get destroyed by it, so to speak. And so this points to issues if you're dealing with a very convective system. Let's say this is perhaps this FCNN ROM is perhaps going to have a little more of a challenge accurately predicting that. Okay, so I'll go into the results from the Suntans model now. And so this ended up, for anybody interested, this ended up being the hyperparameters that produced the best model that we ended up using. And again, I guess something that I kind of always got confused with, because I think it is quite a confusing workflow, is so the spatial modes are constant in time, and we're just trying to predict the time coefficients. That is the key. And I'm not sure if I mentioned this earlier, but I think I did. We're just predicting it for temperature, density, and the U and V components of water velocity. So it's 4 variables that we're trying to predict. And so these here are the 5 spatial modes of these 4 variables. We have temperature down here, for example, and that's just a kind of relatively straightforward PCA. And then these here are the estimations of the temporal coefficients corresponding to the 5 spatial modes. And so the blue line here shows the values that we're using for training, and then the prediction is just this little orange bit at the end, and the exact solution that we're trying to predict is in green. I often find this a little strange because the training data set is significantly longer than the testing data set we're using. So I think this sort of work is just trying to demonstrate a method and whether or not it is functional for our needs. When we reconstruct the fields at the end of the 36-hour forecast that we're trying to predict, we have the truth here from Suntans and the predicted values, and they look really great. This to me was stunning, given once the model is trained, it takes just seconds to produce one of these predictions. and it is of a very complex system that we're trying to predict. I'll just note quickly in terms of training, I think it took about 3.5 minutes for each model to be trained on a GPU, and on CPUs it obviously took a lot longer. I think there were 1,000 different models created and tested for the hyperparameter optimization. So training did take a little while, but it wasn't excessive. This here is over the time of the forecast that we're trying to predict. So from 0 to 36 hours, these here are the relative errors of the three best models that we came up with. And I'll draw your attention to the one on the right. This is the relative error for each variable. And so we have in the green and the orange, we have the two water velocity components, U and V. And you can see they spike somewhere in the middle of the simulation to be above the 5% target that we had. And that's because of a period of strong wind. And when the strong wind came through, it started to make a more chaotic solution that we were trying to predict. And it's sort of hinting at this issue that we had with the Lorenz attractors that moved into a chaotic system. The error started to blow up. Temperature remained really stable throughout it, which was encouraging because temperature is, for something like harmful algal blooms, a really critical component. And density just continued to increase, and good to know what happens beyond 36 hours. We also did effectively the same experiment with the LSTM instead of the fully connected neural network. Here the derivative didn't need to be numerically solved because it's just a different architecture. I don't actually think I've even got any results here, but they were very similar to what the fully connected neural network predicted. So as I said, this work has been submitted to CFDNL, and I don't think it's publicly available yet. It has to go through that process, but we'll be very happy to share it once we're given the all clear from that conference. This here is, I guess, my final slide. So even though this work wasn't about climate is emerging in the last 6 months or so at IBM Research as a really important topic. And so, IBM Research has labs all across the globe and different research groups working on different problems. And I remember there was a time when I learned that there was a group in China, in the Chinese research lab, that was working on weather forecasting in a similar way to we were, but we'd been operating in a siloed fashion for some time. And what's exciting about the more of a climate focus we're having is the consolidated effort around that. So I encourage people to reach out if they have any ideas for collaboration. We're very much open to that. I think we're somewhat like a university department in the sense that our research focus can be quite broad and open to collaboration as well. And with that, I can take questions. PTAC, I can't hear you. Maybe that's my headphones.
Sorry, that was my phone. I put my phone and the Zoom both on mute. I only unmuted one. So thank you so much, Campbell, for your very interesting talk. Really loved it. And I'll encourage everybody to use the chat to interact with all of you speakers here. And I have a question before we get to the question in the chat is, like you used an LSTM architecture for your modeling and predictions, right? So I'm wondering, did you consider using something like an attention mechanism to it, or did you just use the vanilla version? Did you change anything in the architecture, like just so that we know like what was your approach in modeling this?
Sorry, was that to me?
Yeah, that was to you, Campbell. Sorry.
Okay, sorry. Could you repeat? I think I just missed a little bit of it.
Okay, sorry again. So the question I had was like, I saw you had slides where you use LSTM to predict your time series, right? So I'm wondering, did you use any particular modifications to that, like in terms of like maybe adding some attention to it or adding some other, fancy stuff like machine learning stuff to it. So I was just wondering, did you or was it just a vanilla LSTM, package that you used to model your time series? Or did you add any physics information just so that?
Oh, right, yes. So actually the physics information is really interesting. So before I came onto this project, Alberto had been playing with PINs, physics-informed neural networks.
Sure.
And had been finding it really difficult to converge the solution. And I think that seems to be a pretty common problem in this space.
Exactly. Yeah.
Right.
Yeah.
And so we ended up kind of going back to just more of a traditional machine learning framework. As for the LSTM, I know nothing particularly special was done. We played a lot with the time windows, for example, and smaller time windows tended to improve the solution. And I think that for me, it's such a limited amount of data that we were trying to test on. It was one forecast, that there's a huge amount of sensitivity in the solution that would be really great to explore. But that is what we've done. So.
Oh, that's very interesting. Thank you for sharing. So we have a question from the audience. Wyatt is asking, did you get enough input samples through just a sliding window?
For the LSTM?
Yeah. Okay. He says yes.
Yeah. Yes, I think so. Yeah. Let me see. There was. I'll try and if I can I attach a picture to the chat? Do you know?
I don't believe you can, but you can share your screen if you have it available readily.
Okay, I'll try and track it down, which shows sort of the change of the solution as we change the size of the time.
Interesting. Okay, so thank you so much, Campbell, once again. That was a very interesting talk. And then we are hoping to move to our next speaker. This is the last talk of our day and last talk of this session, so thank you so much for sticking around. We have Adrian Albert with us. He is the founder of Terrafuse. And Terrafuse is working towards developing an advanced climate weather and risk prediction product, by some margin, the industry-leading one, using physics-enabled machine learning. Adrian obtained his PhD from Stanford University, after which he was with MIT as a postdoc. Before founding Terrafuse, Adrian was part of the Berkeley labs and did some really phenomenal work there in predicting climate. So thank you so much, Adrian. We look forward to your talk.
Sure. Thank you, Pitak, and thanks again, Adrian. That was a really great talk, and a little bit sad thinking of my hometown in Colorado without snow anymore. I'm gonna miss it.
Probably, well, not in our lifetime. So, but
hey, I want to live that long.
Oh yeah. Well,
but it's true. Yes.
Probably no skiing at the time, though.
All right. So I'm going to finish up here by summarizing what Pitak has said with next steps for those of you who are interested. And thanks for those of you who have been interested enough to stay here for the last 7 hours, as well as those who have dropped in and out as you've had time. So this is part 4 of 5 workshops on tackling climate change with machine learning. Tomorrow, April 30th, we're going to host a cross-cutting methods day. You can find out more about that on the same website you visited for this workshop at climatechange.ai. This will be organized by the same program committee, overarching program committee that's been responsible for this workshop. And you can find out more, again, on our website, which also has a list of resources for those of you who are interested in using machine learning to tackle climate change in a variety of fields and subdomains in climate science and beyond. You can continue engaging with each other and with us on the forum, shown here. And I think that's about it. You should have been prompted when you came into the Zoom to sign up for a newsletter. So please do. We'll have interesting papers, opportunities, and chances for you to look for jobs, share student positions, and otherwise stay connected with this community. So thank you all very much for this attention. We'll stay online for a little bit for last questions for those of you who are still interested and have the time. Thank you.